welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at doing some applications of the derivative, but with our transcendental functions. In previous videos, we've talked about these applications of the derivative. We did these applications with algebraic functions. Then we did some of these applications when we were working with trig and inverse trig functions. Now that we've done all of the transcendental functions, including the log and exponential functions, I just want to take another look at these applications. I want to focus on these three applications in this video. So let's start with using Newton's method to solve an equation. Solve the equation natural log of 3x minus 5 times the sine of x equals 0 using Newton's method. We're going to find the root close to the x value of 3. In order to use Newton's method, we use this formula for finding our next approximation to our root. So we know what x1 is, and then we find a closer approximation by taking x1 and subtracting the value of the function at x1 divided by the value of the derivative at x1. We need this to equal 0 before we define what f of x is. It's equal to 0, so f of x is equal to the natural log of 3x minus 5 times the sine of x. We need the derivative. So the derivative of this will be 1 over 3x times the derivative of 3x, which is 3, minus 5 times the derivative of sine of x is cos of x. When we clean that up, we get this function. So now we're going to find x2. So it will be 3 minus the natural log of 3 times 3 minus 5 times the sine of 3 divided by 1 over 3 minus 5 times the cos of 3. Make sure your calculator's in radian mode before you start plugging any of these values in. I found x2 to be 2.71767, and the number went on past that, but I'm going to find my root accurate to 5 decimal places, which means I will write it down, round it off to 5 decimal places, but I'll use the value in my calculator when I want to do the calculation again. When I use x2, again, the value I've stored on my calculator, in this formula, my next approximation of the root will be 2.70921, rounded off to 5 decimal places. And you can see the difference is getting smaller, so it appears that we're converging to the correct root. So we're going to do the process again using x3. When I use x3 in this formula, I get a closer root, 2.70919. You can see we're getting very close to the root that we want, the accuracy that we want. So we repeat the process one more time using x4 in my formula, and we get 2.70919 rounded off to 5 decimal places again. So we know that this would be a solution or a root to this equation. Let's do an example of curve sketching. All right, we're asked to sketch the graph of this function, and we only want to graph it between 0 and 2 pi. When we're asked to sketch the graph of a function, typically what we do is we find any max-min points, and therefore we find where the function is increasing, decreasing, and we find any inflection points so we know where the function is concave up and concave down. So we need to find those things, plus we need to test them, and then once we have those things, we've got a pretty good idea of what our graph looks like. So we'll start off by finding max-min points. The way that we find max-min points is we take the derivative. This is a product, 2e to the negative x times sine of x, so I need to use my product rule, which says the derivative will be this function, 2e to the negative x, times the derivative of sine of x, which is cos of x, plus, now this function, sine of x, times the derivative of 2e to the negative x, which will be 2e to the negative x, times the derivative of negative x, which is negative 1. We set this equal to 0 to find max-min points, and I'm also going to factor a 2e to the negative x out of both terms, and I'll be left with cos x minus sine x. We're going to use the factor theorem, that says when you have a product equal to 0, the only way that's possible is if at least one of the factors is equal to 0. There's no way for this to be equal to 0. There's nothing that x can be that will make e to the negative x equal to 0. So the only way we'll get a solution is if cos of x minus sine of x is equal to 0. And in order to solve that, I'm going to add sine x to both sides. I'm now going to divide both sides by cos x. And I'm going to replace sine x over cos x with tan x. So x will equal the inverse tan of 1. If you're familiar with your special angles, you might recognize that the two solutions will be pi over 4 and 5 pi over 4. If not, simply making sure your calculator's in radian mode, find inverse tan of 1. Your calculator will give you pi over 4 as a decimal value, and then you have to realize that tangent is also positive in quadrant 3, so to get the second angle, you'd have to add pi to this angle. Once you have these two solutions, you need to test them. What we're testing is whether the first derivative is positive or negative in each of these intervals. So pick any value in this first interval, but start, don't go anything below 0. So I'm going to use 0. I want to see if my derivative is positive or negative when x is 0. This is always going to be positive. It doesn't matter what we use for x. E to the anything, a positive base, when you raise it to anything, it's always going to be a positive quantity. So I'm just going to focus here. When x is 0, cos of 0 is 1, sine of 0 is 0, so 1 minus 0 is 1, which is positive. So the function is increasing in that interval. Then I'm going to pick pi. Cos of pi is negative 1 minus sine of pi is 0, so negative 1 minus 0 is negative. And then I'm going to pick 2 pi in that interval. So again, cos of 2 pi is positive 1, sine of 2 pi is 0, so 1 minus 0 is positive. So the function is increasing in this interval, decreasing in this interval, and increasing. So we know that this is a maximum point, and this is a minimum point. I would then find my corresponding y values, and now I've got those 2 points. Let's next find any inflection points that this graph might have. In order to find inflection points, I need to work with the second derivative. I need to set it equal to 0 and then solve and then test. So I'm going to use this function as my first derivative and differentiate that to get my second derivative. Again, I use my product rule, so the derivative will be equal to 2e to the negative x times the derivative of this. The derivative of cos of x is negative sine of x, minus the derivative of sine of x is cos of x. Plus, now I take this, cos of x minus sine of x, and then I multiply by the derivative of my first factor. So the derivative of that will be 2e to the negative x times the derivative of negative x, which is negative 1. Now, what I'm going to do here is I'm going to factor a 2e to the negative x out of every term. So I'll have negative sine of x minus cos of x. That negative I'm going to apply inside here. So I'll have minus cos of x plus sine of x. When I combine like terms here, negative sine of x plus sine of x is gone, so I'll have negative cos x minus cos x, which is negative 2 cos x. When I bring that negative 2 out, I'll end up with negative 4e to the negative x cos x. Now what I want to do is make this equal to 0 and solve it. Again, e to the negative x cannot equal 0. So the only way this expression can equal 0 is if cos of x equals 0. And in order to solve for x, I take the inverse cos of 0, and the inverse cos of 0 will be pi over 2 and 3 pi over 2. Again, that's a special angle. Now that we have these two values, we have to test. What we're doing is seeing if the second derivative is positive or negative in each of these 3 intervals. So again, I'll use 0 as my point or my x value in this interval. And when I have a 0, remember, e to the any value is always going to be positive, so we're going to have negative 4. Cos of 0 is 1, so this will be a negative. Then I'll choose pi in this interval. Cos of pi is -1, and when we multiply that by -4, that's going to be a positive value. And if I choose 2 pi in that interval, cos of 2 pi is 1 times -4 will be negative. So what that means is the function is concave down in that interval, concave up in this interval, concave down. So those are inflection points. And I need to find the y values, so I just plug these x values into the function to find the y values. Now that we have these important points, let's draw the graph between 0 and 2 pi. So if we were to draw the graph using those points, I also put in the y-intercepts. So we know that whenever sine of x is 0, y is 0, and that will happen at 0, at pi, and 2 pi. So that just gave me a little bit more information. So the graph will be increasing to the max point, decreasing to the min point, and then increasing after that. We'll be concave down until our first inflection point, then it's concave up till our next inflection point, and it's concave down. So that gives you an idea of what that graph would look like. Lastly, let's do an example of an optimization question. The question says, find the dimensions of the largest rectangle that can be inscribed in the first quadrant under the curve of y equals e to the -2x. So I've drawn that curve, and there's infinite number of rectangles that can be inscribed under that curve in the first quadrant, but we want to find the largest rectangle. In order to do that, we need to maximize the area. So if we were to take a representative rectangle, we could describe the length of that rectangle as x and the width as y. So area is what we want to maximize, and it would be x times y. We've got our area in terms of 2 variables. We need it in terms of 1 variable. So we're going to replace y with e to the -2x. So the area will be x times e to the -2x. This is the function that we want to maximize. So this is what we differentiate and set equal to 0. So the derivative will be, we need to use our product rule, so the derivative will be x times the derivative of e to the -2x, which will be e to the -2x, times the derivative of -2x, which is -2, plus this factor e to the -2x times the derivative of x, which is 1. We set this equal to 0. We're going to factor an e to the -2x out of both terms, and I'm left with -2x plus 1. We know that e to anything cannot equal 0, so the only way we'll get a solution is if -2x plus 1 equals 0, in which case 2x equals 1, in which case x equals 1/2. Now we're going to test whether that is indeed a maximum point. When I test, I'm testing the first derivative in each of those 2 intervals. This is the form of the first derivative I'm going to use to test because it's factored. So if x is 0, this will be positive 1, and we know e to the anything is always positive. So we know that the first derivative in that interval will be positive. If I choose, for example, a 1 in this interval, if I put a 1 in for x, that gives me a -2 plus 1, which is -1. This is still positive, so a negative times a positive is negative. So I know the function's increasing here, decreasing here, therefore that's a maximum point. And then my last step is answer the question that the problem asks. It says find the dimensions of the largest rectangle. So the length will be 1/2 of a unit, and the width will be y, and we know y is e to the -2 times x, which is 1/2, so e to the -1. And you can leave it exact, or you can write it as a decimal value. Hopefully now you're very comfortable with finding all the derivatives of algebraic functions, transcendental functions, and you can use that knowledge in a variety of applications. The best way to get good at these applications is to practice them.